So we start our second session. Our speaker is Zhao Zhang, and he'll talk about rigorous results on frustration-free quantum full impact loop model. Please.
Thank you for the introduction, and I thank the organizers for having me here and giving me this opportunity to advertise my recent work. I have benefited a lot from the opportunity, from the learning opportunities and the discussions. So, without further ado, let me start by saying this is a work that started where Henrik Rossing and I were both at Nordita, but shortly after we started, we moved to different places. I'm now at CISA and Henrik is at Niels Bohr Institute. So hopefully this manuscript will appear this Friday on arXiv, so you can check it out. I'll start by giving some background on the motivations for studying this model, and specifically was twofold. We wanted to do something about the ergodicity of this kind of 2D models with within some constrained Hilbert space, and also we want to see if there is any exotic entanglement entropy scaling in 2D models. And then I will discuss the Hilbert space fragmentation, and specifically within each Krylov subspace, there are exact eigenstates due to the frustration freeness of the Hamiltonian, and I will show how we exactly computed the entanglement entropy between half systems, and we finally gave a rigorous proof on upper bound on the spectral gap that goes to 0 in the thermodynamic limit. And finally, I will talk about a few open questions. So just to briefly review the ergodicity, both in classical and quantum world, to me, I find it to be one of the most fascinating things about statistical physics, just the fact that you can evaluate the long time average of some observable by its average in an ensemble. And in the quantum systems, if this were true for any initial state, then since any state is a superposition of some eigenstates, it necessarily means that all eigenstates of the Hamiltonian themselves are thermal and ergodic. And we know now that there are two examples of strong violation of ETH. One is the integrable system, and the other is many-body localized system. Both of them have infinite number of conserved charges, so that the ergodicity cannot extend beyond the constraints by those charges. And more recently, there are also examples in weak form of ETH violation. In the classical world, this is showing this kind of billiard or stadium, where if you choose very carefully where your initial velocity and position is, you will keep going through these trajectories called the scars, and you never leave these subspaces. And this is recently found in quantum counterpart in this Rydberg blockade systems, where two neighboring sides of Rydberg atoms cannot both be simultaneously in the excited state. So this way the Hilbert space is constrained by a number of dimensions that grows as the Fibonacci sequence. And so naturally, one question you can ask is, are there any 2D counterparts that may demonstrate this weak ETH breaking phenomenon? And if you are familiar with the quantum dimer model, the answer is, of course, yes. In fact, we found this posting on this physics stack exchange forum where someone asked whether this quantum dimer model is ergodic or not. And by ergodic, it means these rocks are Kivotson type of Hamiltonian, where if you have two parallelly aligned dimers on a plaquette, you can do a ring exchange and rotate it by 90 degrees. So this will keep you always in the constrained Hilbert space of dimer coverings, but this question of whether such a move is ergodic or not was never satisfactorily answered. Someone says, based on limited numerics, there is evidence to believe, to assume the ergodicity, and some more careful statements have been given rigorously on a specific topological sector. And in fact, one of the answers to this question was hidden in the appendix of some spin liquid paper, where they show that in the zero flux sector on the periodic boundary condition, you can and the proof roughly goes like this. So this dimer configurations allows a natural height representation, and the height changes by +1 if you go around the vertex without crossing a cover bond, and if you cross a cover bond, then you change by -3. So the argument says, given any height configuration, there is always maximum height. A plaquette with maximum height and a plaquette with you will find that the height plaquette is flippable if its height local minimum or maximum. So a global maximum or minimum naturally means it's a local maximum or minimum, so that there are always these kind of and all of them can lead to eventually one state called the ideal state, where the height just alternates between neighboring plaquettes. So if you flip any of them, you will go to the other, and you can show that all these other height configurations can subsequently arrive at that one. So this all sounds very nice, but first of all, it only works for the zero flux, meaning that going around a non-contractible loop around this lattice, the height doesn't change. And also this proof in that the appendix of that paper was actually for so-called two dimers, which means the FPL, fully packed loop model. So, yes. Quantum dimer just means that you have an off-diagonal term in the Hamiltonian where you can go from one local plaquette configuration to another, so that the ground state of such a Hamiltonian is the uniform superposition of all dimer coverings. I'll explain in more detail later, but here in this question, you already see that this proof doesn't work for many exceptions. These two are both examples where you have no flippable plaquette at all. So they are isolated in the Hilbert space. And on a completely separate note, the other motivation of this studying these models is that we a few years ago we studied this one-dimensional spin chain that can be mapped, whose configurations of spin ones can be mapped to a Motzkin walk, or if you go with spin half chain, you can be mapped to the Dike walks. And we found with some quite natural frustration-free Hamiltonian, these ground states of these models have very exotic aerial law breaking entanglement scalings. And we have attributed this kind of entanglement behavior to the fact that there's a well-defined notion of height, because you can establish you can entangle pairs of spins that are at the same height by matching their colors and things like this. So how does this how do you get a quantum Hamiltonian from such a classical or StatMech or combinatoric objects? The thing you do is by designing a frustration-free Hamiltonian. So frustration means usually if two neighboring terms in the Hamiltonian are not commuting with each other, then the ground state of the Hamiltonian will not be the lowest energy eigenstate of either of them. And so what actually is the ground state will then be a state where neither of the two terms are perfectly happy, but neither are two are equally unhappy, so that they compromise a little bit. But with a frustration-free Hamiltonian, you don't need to worry about this. So you can, in this case, design these projectors that projects onto eigenvalue 0 if these two locally different configurations comes with the same weight. And if you impose these projectors everywhere along the chain, then in the end, what you have is a uniform superposition of all such kind of configurations that between each pair, they are only locally different. So the second motivation is then how can whether this can happen in 2D or not? Yes. This is for a fixed boundary condition. Yeah, so no, for periodic you would well, you will still be frustration free, but you won't have a good notion of height, because you don't have a reference point. And the outcome of the study of our new model that I'm going to talk about is that naively this doesn't carry to 2D. So what is the way to define height, a notion of height in 2D? And when we were thinking about generalizing these height models to 2D, one difficulty that comes is that you have between the height difference of two sides on the lattice, you have multiple paths to connect them. And it seems a little bit of difficulty to make all these differences consistent. But this is naturally avoided by the 6-vertex model, because around any vertex, however you go around, there is a U1 Coulomb gauge phase of this height field. So however you choose the height, there will never be any ambiguity in the height. And this 6-vertex model, when you choose this ABC type of vertices ways to be equal, a uniform superposition of 6-vertex model is also a uniform superposition of fully packed loop models. And further, if you enforce domain wall boundary condition, then there's also a one-to-one mapping to the alternating sign matrices. So this, here we already see the resemblance to the 1D constrained Hilbert space models, that this Hilbert space dimension grows instead of some exponential of some constant, it grows as an integer sequence that has this symptotic scaling. Now, how do we make this model quantum? The thing we want to do is that every time you act the Hamiltonian on a state, you remain in the Hilbert space. So you always go from one fully packed loop to another fully packed loop. And this you can do by locally changing the covering of one plaquette. And further, I have implemented this off-diagonal terms in terms of the projector, so that all we care about is that the ground state is a uniform superposition. And we don't know anything about the excited states. But the reason to do this is that now we have all the properties of the ground state for free from our results in the classical StatMech problem, such as the 2-point correlation functions, equal time correlation functions. This will always be the same as in the classical StatMech problem. And we also enforce, so in this model, we enforce the constraint that the Hilbert space remains in the fully packed loop or 6-vertex configuration by requiring that if any vertex is covered by more or less than 2 bonds, then you will come with an energy penalty that is much larger than 1. I should mention that there are also alternative ways to do this in a frustration-free fashion, but then this like in the AKLT construction, where you do this by some underlying spin degrees of freedom. But in that case, these fully packed loop states will have overlapped. Their wave functions will have non-zero overlap. Well, in our construction, they are all orthogonal to each other. So you can also enforce the domain wall boundary condition by incurring an energy penalty if the boundary configuration is different at any point from the domain wall configuration. And then the outcome is that the ground state will be an equal superposition of all fully packed loop states with the domain wall boundary condition, and the normalization is exactly the number of alternating sign matrices. So in the case that n is equal to 4 or 3, you have 7 number of them, and this is what the ground state looks like. So as I already...
Can I ask a question?
Yes.
So how does the Hamiltonian look like in terms of spin 1 operators?
Yes.
You show the relation between the spin 1 configurations and the arrow configurations, right?
Sigma and R. If I got your question correct, you're asking how would the construction look like with spin 1 degrees of freedom?
Yeah, exactly.
Yeah, so basically you can decompose each spin 1 into a product of spin halves, and then design a projector to require 2 spin halves on neighboring sides to form a singlet. And there are multiple ways to do that around a vertex with 4 bonds, and you just need to have a product of all these projectors so that of the 6 different choices to choose 2 from 4, and so that any particular choice being annihilated already give you the lowest energy. I know this sounds a bit abstract, but I can explain later in more detail.
Okay, thank you.
So this there is a dual representation on the dual lattice with the height degrees of freedom, and in this case, the height, the Hamiltonian looks even more similar to the Rydberg blockade Hamiltonian, where you have to have all 4 neighboring plaquettes to have the same height below for you to flip this and decrease the height, or you have all 4 of them above you for you to flip and increase the height. And so the ergodicity breaking of this Hilbert space is uniquely labeled by the boundary configurations. And since we know that the boundary heights, if you go once around the whole lattice, must go back to the same height, you need at least 1 kink along the boundary. And if you only have 1 kink, then the only possible way you can have is that this kink happens exactly at 2 opposite in corners. So this green color, the opacity of the green color denotes the height. So if you go around here and to there, you increase monotonically, and then you decrease monotonically. And you can see that this one configuration has no flippable plaquette, so it's isolated in the Hamiltonian. And the next, you can never have 3 kinks, because you would then you alternate between monotonic regions that increases or decreases. So the next you can have is 4, and with 4 there are 3 ways that you can have a product state, eigenstate, and these are the roughly loosely speaking saddle point configuration. Yes, a kink is the boundary between monotonically changing heights, segments of monotonically changing heights, if you count the height along the boundary. And this is the case when you have 4 monotonic regions that cover the entire square lattice. But if they don't cover the entire lattice, you have a smaller region in the center that is also subject to the domain wall boundary configuration. So what can we know from this? We know that some part of the spectrum of a smaller system will always be present in a larger system with the same domain wall boundary condition. So there is embedding of spectrum between lattice systems of different sizes. It's kind of like the nesting Russian doll here. If you look at these square regions that are not covered by the monotonic regions, and if you have more than 4 monotonic regions or more than 4 kinks, then the only way you can have a product set eigenstate is where 2 parallel sides are monotonic, and you can arbitrarily change in the perpendicular direction. So this exhausts all the possible product state eigenstates, and they all come with eigenvalue either 2n or 2n minus 2 because of the boundary configuration. So all the other somewhat ergodic states form eigenvalues. They give one eigenfunction that is the equal superposition of all the configurations in their Krylov subspace. Ergodicity just means that when you act the Hamiltonian on one state, you can get another state, and all these states will be in the same subspace. So within this subspace is considered ergodic, so that by time evolution, you will be able to reach all these states in this subspace. Yes, these subspace are ergodic by themselves, but they are disconnected from the other subspaces. And this is all, but this is a property of the Hamiltonian. It's not ergodic enough that you can reach all these other states given a particular initial state. No, any state. Oh, but here I can only give the exact formula for the lowest energy eigenstate for each sector. Within each sector, they will have exponentially many eigenstates, as large as the dimensionality of the space. Yeah. No, because we enforce the we add these boundary terms to favor the domain wall boundary configuration. So that one will has energy 0, but if the boundary configuration changes, then you will be in another Krylov subspace, and all those are lower bounded by the energy penalty from the domain wall boundary condition.
Excuse me, can I ask a question?
So what do you mean by?
Okay.
No, I don't think the. Well, but this space is the I see your point. This somewhat natural basis in that it is the product of local configurations. Yes, online questions. Is there an online question?
Yeah, can I ask a question? So what's the ground state degeneracy of this model?
It's unique. The ground state is unique because of the boundary terms in Hamiltonian.
But are these product states excited states?
Yes, because they are, well, the degeneracy was lifted by the boundary terms. And the reason that they become disconnected setters is because the boundary Hamiltonian are diagonal. You don't have, well, basically you don't have ways to flip a plaquette that has only 3 edges.
Okay, thank you.
Yes, and we have established this ergodicity within each boundary configuration by using a mathematical induction. So assuming, well,
then from the Perron-Frobenius theorem, the uniqueness follows, right?
From the
Perron-Frobenius theorem. Yeah, that's what you used for the proof of the uniqueness, right?
From the,
how did you prove the ground state that the ground state is unique?
We proved that by proving the ergodicity, because all these states are related by some term in the Hamiltonian to each other. So the only way that all these projectors have eigenvalue 0 is the unique one.
I see.
That each come with, yeah, it's the Perron-Frobenius ground state where all of them have or each component has a coefficient 1.
Not necessarily 1, right? They have the same sign.
They have the same sign, but in this case, because
in this case, I agree. Yeah.
Okay, so for the sake of time, I guess I'll skip the proof, but it's by mathematical induction, and it works for arbitrary boundary condition as long as it's not the subspace itself is not one-dimensional, in which case the ergodicity fails. And then we computed the entanglement entropy between 2 half systems. If you cut in the middle with some recurrence relations on enumerating the number of configurations of half systems that are fixed on 3 sides being domain wall and 1 side being free. And we found that the entanglement entropy grows as an area law, and we also found that this constant gives the topological entanglement entropy of a Z2 topological order. Although, as you see later, this is a gapless phase. So we don't know what is the reason really behind this topological entanglement entropy. But the fact that this is scaling is area law says this constant is protected by local perturbations from these kind of. How much time do I have? When do we started? 35. Okay, so I have 10 more minutes. Okay, sounds good. Yeah, so we don't really understand this topology here very well, and probably that is also because we don't understand how this Hilbert space fragmentation is different or equivalent to topological sectors. And with domain wall boundary condition, you can't really define, you can't really put it on a torus or a cylinder. So at this point, it's not really clear to us what is the reason behind this topological entanglement. And so how to show that this state is a gapless phase that doesn't allow a topological phase? The way to do this is by constructing a 12-wave function that is orthogonal to the ground state. And you can do this by adding a twist to the ground state superposition. So you can order all these fully packed loop configurations by the total height across the entire lattice. And here we call it volume, as if you just integrate this height function over the 2D square lattice. And then there will be a minimum height and the maximum height. And the number of configurations about the average between them is actually symmetric, so that you can make the superposition on one side all comes with plus sign, and on the other side all comes with minus sign. So this way, when you take the inner product with the ground state, then these two parts will cancel out, so that you have a zero overlap with the ground state. And this doesn't affect the normalization of this state, because the -1 square to 1, so you still have normalization being the number of alternating sign matrices. Next, we just need to show that the expectation value of the Hamiltonian on this state is vanishes in the thermodynamic limit. And to do that, we have to just enumerate the number of states that are close to this cut, because all these other configurations that's deep in the bulk of these two sets are already superposed in a way that satisfy each local projectors. So the only non-zero contribution can come from the Hamiltonians that take you from one set to the other. And the way to do that is to look at one particular configuration near this boundary. And this is one example of them. You can see that all these four corners outside the center are frozen. They have no flippable plaquettes. And inside, half of them are these squares with all four bounds covered, and the other half are actually mobile in the sense that you can flip independently all these heights with all these plaquettes with height 4 and 6. And you see that the middle configuration in this axis, with the average volume, has exactly n squared over 4 number of flippable plaquettes. Out of those, more or less half has the height smaller than average 5, and more or less the other half has the height just above the average height. So you can arbitrarily choose any half of them being on one side and half of them on the other side, and this will give you exactly one configuration near the boundary. And this number is called force m choose m plus 1 over 2. And for each such configurations, how many ways you have to go across the boundary to the other side. And the way is exactly the number of plaquettes with a surplus, in this case is the plaquettes with height 4, because there are one more plaquette with height 4 than those with height 6. So then the way to compute this expectation value is where this, instead of summing over all these fully packed loops, you just sum over all those that has heights just above or below this average. And this is exactly the number of such plaquettes that are flippable in one way times the number of such configurations. So this second factor is the number of these dots on this set, and the first number is the number of bonds that each these dots connects to the other side. So this, if you normalize with the number of alternating sign matrix, you'll see that this is exponentially going to 0 in the larger limit. And therefore, we have proven that this is a gapless space. So so far, these all have been as rigorous as possible. But next, I will state some speculations that are not so rigorous. So we know that these fully packed loops come with each of them with a particular link pattern, which you can lay out in one dimension that has this kind of dike walk description. And there are these one-dimensional models that you act on the space of dike walks, which has an interesting tensor network representation. And this tensor network representation is holographic in the sense that all the physical degrees of freedom are on the edge, and these tensors contract inside the block. This, by the way, is almost exactly the 6 vertex configuration here. So our ground state, as well as the frustration-free excited states, are also described by these projected entangled pair states. And speaking of holography, we know that this fully packed loop on square lattice comes with Wieland dihedral gyration symmetry. Is this not playing? Yes. So this is what the gyration operation does. You can see that it leaves the flippable plaquette unchanged. And so if you, instead of the current domain wall boundary, instead of the current way of enforcing the domain wall boundary condition, you can also have one that just checks if 2 neighboring bonds are simultaneously covered or not. And in that case, the total Hamiltonian will commute with the Wieland gyration operator. So we know that the eigenvalues of the gyration operator will be good quantum numbers. So you can diagonalize the Hamiltonian within each sector with a fixed eigenvalue of gyration operator. And there is also, so it's interesting to see if there is any chiral Ash mode. And I mentioned here that in these rigorous results on the gap of frustration-free Hamiltonians in 2D, there is a corollary that says there are no gapless Ash modes, in the sense that the dispersion decays as 1/n. So it's exactly the case that we have here. So it's interesting to see what is the dispersion relation of the chiral Ash modes here. Okay, so this is the open questions that we more or less don't have the answers to. First, we have from the very beginning constructing this model to mimic the 1D Rydberg blockade system. And so the natural question to ask is if there exists easy to prepare, experimentally easy to prepare initial set that is lowly entangled, that will have this kind of revival overlap with the initial state. And also it's interesting to think whether adding a connected term in some way to the boundary will, of course, it will reduce the ergodicity breaking or the number of Krylov subspaces, but it's interesting to see how one can implement a periodic boundary condition with fully packed loops. And also whether one can increase the entanglement entropy scaling by adding a color degrees of freedom or doing a Q deformation. And in this case, if you deform the projectors with a parameter Q, then it will correspond to introducing an anisotropy in the lattice. And there will be a duality between Q and 1 over Q, which favors aligned bonds in one direction or the perpendicular one. And I already mentioned there is a way to construct the spin Hamiltonian to enforce the constraints. And it's also possible to discuss similar constraints on other lattices, such as hexagonal lattice, but with dimers instead of fully packed loops. So with that, I'd like to thank you for your attention. Yes, that's a good question. So in this, in the current model, we didn't really do that other than, adding this abstract energy penalty. But we want to keep things simple so that we don't complicate with unnecessary details. But one way to do this is, for example, you can have spin 1 lattice and you look at the spin 1 as triplet combination of 2 spin halves, and then on each neighboring sides you also have these pairs, and you can take these two and these two to form a singlet, or any other pair of 2 out of these 4 to form a singlet. And you can design Hamilton, for example, this by writing this SU2 symmetric Hamiltonian. Maybe I shouldn't go into the detail, but the point is that you can require these two to form a singlet so that these two, the sum of these two spin ones, they will never be in spin 2, right? And then you can have a projector like that acts between this neighbor, another acts another neighbor. Of course, this will look a bit complicated, but it is possible to at least write down such a Hamiltonian spin ones. To, of course, how realistic this is to experiments. This is not easy even in the one-dimensional case. But people have done this for 1D case, and they have done this for the quantum dimer model in 2D. And in this case, there is also a way to do it. These are called the Klein Hamiltonians.
More questions?
Thank you. So I'm wondering about the choice that you started with. You choose all the weights of all 6 vertices to be 1, or not necessarily 1, to be equal. So I mean, this is how necessary is it in this construction? Could you choose like different?
Because our kinetic term relates different plaquette configuration, right? And so with this, you can have all these FPL configurations to be uniform superposed. But uniform superposition of FPL does not mean well, it means a uniform superposition of 6 vertex. But if the 6 vertex weights are different, then you cannot, at least you cannot define a projector in terms of fully packed loops to enforce their different, to enforce a weighted superposition of 6 vertex configurations. Because 6 vertex, what you do is that you are rotating the arrow of all 4 bonds around the plaquette. But if you want to change the configuration of vertex, you need to worry not only about these 4, but also these, and others. So it becomes more and more non-local if you want to do something like this. In fact, I think however large a radius you choose, you cannot do that with the 6 vertex configuration.
More questions? If not, let's thank the speaker again.
I have a small comment. Okay.